Hello, everyone. Wherever you are in the world, I hope you and your loved ones are healthy and safe. My name is Randy Bell, and I'm the director of the Global Energy Center at the Atlantic Council. Thank you all for joining us for today for EnergySource Innovation Stream, where we aim to highlight new energy technologies with the potential to reshape the global energy system. Today, we will be hearing from Robert Doe, President and Chief Executive Officer of SGH2. We'll discuss the process of green hydrogen production from biomass gasification and SGH2's plans to develop the world's biggest green hydrogen production facility in Lancaster, California. Before we get started, two administrative details. First, you can follow us on Twitter at AC Global Energy and use the hashtag InnovationStream. Second, after Robert's presentation, you can submit questions through the Q&A function on Zoom, and we'll try to get to as many of these as I can. If you're watching on another platform like YouTube, unfortunately, we cannot take your questions. So please let me welcome Robert Doe to the Atlantic Council. Robert, thank you so much for joining us today.
Hi, Randy. Thanks for inviting me. It's an honor and a pleasure to work with the Global Energy Council.
Great. Well, thank you. Really excited to learn more about your green hydrogen project out in California. I'm wondering, how has COVID impacted the timeline for this project?
Well, actually, this question has a lot of meaning to me because, I'm also an MD as well as a biophysicist. So, I'm still a licensed physician. I'm well connected into the medical community. And it has been one of the toughest time, I guess, for the medical community in dealing with this. So from that standpoint, my message is everybody, please stay safe, social distance, wear your mask. It's not over yet. There's still a lot going on here. It's a very tough, very virulent disease that we have yet to control. So that's my message of safety. As far as business is concerned, I think what COVID-19 did to all of us is that with this shutdown, everybody start noticing one thing, that there's less transport, less people going out, doing things, less airplanes, less shipping. And what we see is cleaner air. And cleaner air, less emission is so obvious that, this is a time where a lot of people reflect, well, this is what we want. This is what we want. And I think you see that triggering through the community, whether the investment community, the energy community, everybody start focusing on how do we do this? And then you see even the Recovery Act, right? The European Union putting in Recovery Act, emphasizing that it's going to go into green energy, reducing emissions. So I think it is really in a silver lining, this COVID-19 for us who's concerned about climate change.
Yeah, I mean, I've never seen so much interest and so much policy pressure, particularly as you said, coming from Europe, and with hydrogen being a major part of the plan and a major area for investment. So we're really looking forward to hearing about your solution to what is a real challenge: is getting the hydrogen production off the ground and having enough so that you can actually scale the use case for it. So why don't we get started with your presentation? Roger, if you can go to the PowerPoint, that would be great.
Thank you, Randy. Well, again, thank you to the Atlantic Council and the Global Energy Center to give us an opportunity to present what we call greener than green. And I guess the first question people ask is, what do you mean by greener than green? And for people who are in the know, what we're talking about here is negative emissions. And what is negative emissions? Well, there's a whole industry, they call themselves negative emission technology, or NET, which I'm not going to go into. But what it does mean is that we can get lower emissions than by utilizing green energy alone. For example, when you take waste, which normally goes into a landfill and emits a lot of methane, or you have dairy waste that goes into the landfill and land application and create a lot of methane. Methane is 20 to 30 times more potent in the heat capturing than CO2. So by avoiding all of that methane release from landfill, you are capturing more CO2 and avoiding CO2. So now you're considered negative emission. And I'll talk to you a little bit more as we go along. But that's what we mean by greener than green hydrogen. Next slide. So when you talk about hydrogen, I think what people should know is today there's a lot of hydrogen being produced already. I'm talking about 100 million tons of hydrogen is already being produced today. And almost 99.5% of that is made by fossil fuel. And when you talk about fossil fuel, 70% of that hydrogen is made from natural gas. We call that gray hydrogen. So you steam reformation of natural gas create gray hydrogen. The other 30% of hydrogen that's produced in the world today is actually made from gasification. But they are gasifying coke, pet coke, or they're gasifying coal to make hydrogen. For example, our engineering partner, the Fluor Group, just completed building one of the largest gasification plant in the world to make hydrogen in India. And they're using coal and coke to make what we call brown hydrogen. And this brown hydrogen is going to go into the refinery run by Reliance, the big refinery in India. So this here is brown hydrogen. And so what it shows to you is gasification technology to make hydrogen is a well-proven technology and done at very large scale. This project by Fluor generates 50,000 tons of CO2. 50,000 tons of hydrogen a year. And I think that shows you the scale of hydrogen that can be produced from gasification. There's no electrolysis plant in the world that has gone anywhere near this size. So this is what we're using. We're using gasification, which is an industrial platform that's well proven to make hydrogen. But instead of using fossil fuel like coal or coke, we replace that with a biogenic feedstock like biomass and waste product that are biogenic in nature, which means the hydrogen that we're pulling out at the back end is basically green renewable hydrogen. Now, the California state has issued a roadmap for California hydrogen production for the next 10 years, from 2020 to 2030. And they have confirmed that only 50% of the hydrogen that can be produced in California in the next 10 years can be made from electrolytic or green electrolysis to make hydrogen. The other 50% has to come from gasification of biomass and a smaller part from biogas. So that shows you the future of green renewable hydrogen is not depending only on one technology like electrolysis, but multiple technology in order to meet the demand. Next slide. So what is it that we do in our technology? And what we're doing here is utilizing gasification technology. For a lot of people who don't know what gasification is, I will give you a very brief explanation of what gasification is. So when you heat something up with no oxygen, it's called pyrolysis. And when you add a little oxygen, it becomes partial oxidation or gasification. And if you add a lot of oxygen and a lot of air, then you become complete oxidation or combustion or burning. Okay, so that's the 3 steps when you heat up something. Pyrolysis in the reducing atmosphere, no oxygen. You add a stoichiometric, that's the word, a limited amount of oxygen, then you create gasification, which generate carbon monoxide and hydrogen. And then when you go all the way with a lot of air and oxygen, you go combustion. And that's when you create CO2, and that's when you create steam, and that's when you burn something. So for us, utilizing gasification is a well-known technology. But the problem with gasification up to now, when they use oxygen, any technology where you use fluidized bed gasification or you use blast furnace gasification, the problem is a limited temperature that you can generate, what they call autothermal, meaning the amount of heat that you generate from the oxidation of the hydrocarbon would only get you to about 2,000 degrees centigrade. To a lot of people, they think it's very high. But to us, that's not high enough. So what we did was we added plasma torches, which is a technology developed by the US NASA program to test heat shield material for spaceship. And it's the only industrial heating source that can allow you to raise the temperature up to 4,000 degrees centigrade. So that becomes what we call allothermal, meaning we have an external source of heat to add to the autothermal. It allows us to increase the temperature of operation. Now, why is that important? That's important because that allows us to completely break down the product that comes in. So if you take waste product and you have plastics and you have car tires and you have all these different things, you put them in 4,000 degree, you're able to completely gasify, depolymerize all the hydrocarbons and release them into the syngas. Let me show you a little bit more how that's done in the next slide. So when you look at an image of the gasifier, what you see there is what we call a fixed bed gasifier. And a fixed bed gasifier, meaning you have a bed of feedstock, we can feed the waste in, it would just fall down to the bottom. We add oxygen, so we create that autothermal heat. And then we added those plasma torches to increase the heat. And what that does is it allows us to completely break down anything that comes in at 4,000 degrees centigrade, including what normally comes to the bottom as ash or char. These are solid carbon. The temperature is too low to break that bond, but at our temperature, we're able to completely recuperate all the solid carbons and remove that. So at the bottom of our reactor, you can see the temperature is 3,500 to 4,000 degrees centigrade. And the waste will come down into the gasifier. And then we have a counter current of hot, very hot air going up into the plenum, where it's thermally cracking it, removing all the possibility of creating tar. Tar basically is the Achilles heel of all gasification technology. And that's the problem with every gasification up to now. They are producing a lot of tar, which is basically long chain hydrocarbon, which can take up to 15, 20% of the carbon and hydrogen that you have in your feedstock. So you're losing a tremendous amount of energy, and then you have to create a tar removal system. Next slide. So what happened at the end from a molecular level, what we're doing here is we're breaking down all the waste, what we call hydrocarbon, because basically they are hydrogen, carbon, and oxygen. We're breaking down into individual molecule, and we are reforming it into two molecules, basically hydrogen and carbon monoxide. It makes up about 87% of our gas, typically 43% hydrogen and about 45% carbon monoxide. And what that does, and without any tar, and this is the key, because now we have a very rich syngas that has a high amount of hydrogen. And you're looking in the second picture, we have a scrubbing system afterwards. Why do we have a scrubbing system? Well, if you have a lot of hydrogen and you're taking plastic product, which has a lot of like PVC, a lot of chlorinated products. So you have chlorine, which immediately attached to your hydrogen, and you have acid gas, HCl. If you have sulfur, like in your car tires, the sulfur will come in attached to hydrogen and makes H2S or COS. These are acid gas that need to be removed. And of course, the process of removing them is very simple. You scrub them out with a base, and then you're able to recover either sulfur cake or you recover it in a salt form. But then you have a pure CO and H2. So what we do with that then, in the last bottom picture, we put them into a water gas shift reactor. This is a standard technology where you shift all the CO by using steam and turn them into more hydrogen. And then from there, we just put them to a PSA, which is what we call a pressure swing absorber, essentially a purification system that we can purify the gas into 99.994 times purity. It has to be 994 times because that's the purity that you need to get into a fuel cell vehicle. So that's essentially, a very simple process. Feedstock coming in, we dissociate it. We're basically doing what we call here chemical recycling. We recycle all the waste product by taking the chemistry out and recycle them into hydrogen. And if the source of the feedstock is biomass, biogenic, then the hydrogen we're generated is green, renewable hydrogen. Next slide. Now, this is a slide that I'm trying to concentrate the most time in because this is a very important slide. Everybody talks about making green hydrogen and then immediately think of that as electrolysis. What is electrolysis? Electrolysis is when you break water to make hydrogen. It is probably the most elegant way. And that's why a lot of people are attracted to make hydrogen from electrolysis, because there's water everywhere, right? And you just break it up and you use, green energy like solar and wind to break it up. And then you have hydrogen. I mean, it sounds like perfect way to solve our problem, knowing how great hydrogen will be. The challenge here is thermodynamics. It takes a lot of energy to break up water. And so for 1 kilo, to make 1 kilo of hydrogen, you need 62 kilowatt of power. Doesn't matter where that power comes from. It could come from wind or solar or power plant, doesn't matter. You need 62 kilowatt, and then you need a lot of water. You need deionized water, not any kind of water. It has to be clean, deionized water. And you need 8 gallons of it in order to make 1 kilo. So when you add the cost of building a very large wind solar plant, and you need 62 kilowatt to make all this water into hydrogen, the problem is those solar and plant and wind farm would only operate when there's the sun shines or the wind blows, which means 25%, 30% of the time. The 75% of the year, those plants would sit idle. The electrolyzers not making anything. So when you put all of that together, it makes electrolysis hugely expensive. Today, the cost of making 1 kilo is approximately $10 to $13 to make from electrolysis. And that is assuming cheap solar and wind. So the projection today for the market is by 2030, when you build massive electrolysis plant with 2-3 gigawatt of wind farm, increases the capacity factor maybe to 50%, you can drop it down to $5. The other way to make hydrogen, like I said, is gray hydrogen. And look at the gray hydrogen cost. When it's cheap, it's $2. When natural gas is expensive, it goes to $6. We can make the hydrogen with our project at $2. Next slide. So the key here is there are a lot of industries that need hydrogen. We're talking to the largest cement plant in the world who want hydrogen and our gas to be built next to them. We're talking with the largest natural gas company in the world who's like to inject up to 10% of their natural gas or their natural gas power plant with 10% hydrogen, 20% hydrogen. So the missing link to decarbonization is hydrogen. Next slide. Today, like I said to you, 99% of the world, hydrogen, that's $183 billion of hydrogen and about 850,000 tons of CO2. So the idea, we need to replace those brown hydrogen as well as create hydrogen for the new market demand that I mentioned to you. From transport, which is 40% of the hydrogen, all the way down to cement plants, steel mills, power plant, decarbonizing the natural gas grid. Next slide. So the challenge is, how do we get there? And the idea is to get there by designing a plant that would make you the cheapest amount and the highest amount of hydrogen at the cheapest price. Next slide. We are building our flagship project with a consortium of, I would consider, the top companies in the world to build a plant in Lancaster. Next slide. This plant will take in 40,000 tons of waste. In this case, we're using recycled mixed paper. And I think that this is another issue that we can solve, because we have all been recycling paper and plastics in our little bins and people take it out and they sort it and they try to recycle it. What they normally do, the recycling company, is ship them to China. But for the last 2 years, the China are banning all the import of any recycled waste from the US, whether it's plastics or paper. So right now, there are millions of tons of this product all over the US and Europe with nowhere to go. We are going to take that recycled mixed paper and we're going to make 11,000 kilograms of hydrogen a day, which is the largest green amount of hydrogen being made today anywhere. Next slide. The market is massive. I mean, this slide is not up to date, but we're talking with groups from India all the way to Australia and multiple plants in Europe, because Europe is really hard pressed to start decarbonizing. And we believe that the market penetration would depend on more cost competitive hydrogen. Next slide. So I know I rushed through this presentation. We can go into more detail to discuss. But what I wanted to close this presentation is to remind you of multiple things. Number one, there's more than one way, and we need to have more than one way to make green hydrogen than to do it just with electrolysis. And it has to be cheaper in order to penetrate the market. It has to be cost competitive with fossil fuel, which we believe that we can do it today at parity. And lastly, the key here also is to think of circular economy by utilizing our waste product, waste, agriculture waste, forestry waste. All of these are waste material that we can recover through this chemical recycling and produce hydrogen to decarbonize our industry. And one of the most exciting thing that I wanted to say that we're working on right now is taking the biomass woody waste that you get from forest thinning and forest trimmings in California, working with the largest firefighter association, because there will be millions of tons that need to be done to prevent further forest fire. And we can take all of that and turn them into hydrogen. So for me, that is what we like to do. Produce a green source of energy to replace fossil fuel, while at the same time doing a circular economy, recover the material that's already here without digging anything up from the ground. So thank you very much today, Randy, for giving us an opportunity to present this.
Robert, thank you so much. That was really, really fascinating. And Roger from our team, thanks for running that slide deck. So Robert, what's fascinating to me is we've been looking into questions about hydrogen recently is the ability to actually produce enough green hydrogen. As you noted, there are cost issues associated with electrolyzers right now, but Michael Weber from Engie noted that the price is coming down. I think that's worth noting to the audience. Might even be lower in some places than what you had on your deck. But there is, I think, a problem about generating as much green hydrogen from electrolyzers as what's really demanded to create a hydrogen economy. And there's lots of different conversations about how to solve this, but I like that this is one piece of that puzzle. We have tons of questions coming in, which is great, but I have two of my own first. So first, what is the end use for the hydrogen that you plan on producing in Lancaster, out of the Lancaster facility?
Thank you. Yeah, I was rushing out the presentation. I wasn't able to say more clearly, but we are 100% of our hydrogen produced there will be used to feed into hydrogen stations. There will be hundreds of hydrogen stations that's going to be built out over the next 10 years. And all of our hydrogen will go out to provide directly into those hydrogen stations in California. So they will be exclusively used for transport.
Ground transportation, right? Do you think that's more on the heavy trucking side, or is there a market for light duty vehicles?
Interesting. The majority of them will be for light duty. Heavy duty is picking up, particularly with this 2024 regulation from California for zero emission trucks and buses. So we anticipate there would be an uptick demand in the HD side, but probably, by 2024, 2025. So we're already planning to start building the second plant to supply the heavy duty transport.
Got it. Very, very interesting. Okay, one more question from me, and this is going to perhaps indicate my lack of technical knowledge. But you say one of the products is carbon monoxide. What do you end up doing with that? Is that vented, or is that a product that you can sell? If it is vented, do you have any ozone issues?
A great question. So yes, all gasification produces CO and hydrogen, and so anybody can say that they can make hydrogen. The question is only the quality of the syngas. How much CO do they get? How much hydrogen do they get? The volume percentage. Like I told you, we are getting almost 90% of them in CO and hydrogen. And why? Because of the fact that we are able to optimize the process. And CO and hydrogen actually are the two compounds that are most stable at high temperature. So being a high temperature system, we almost extract more CO and hydrogen. Now, what we do with the CO after we come out of the gasifier is we actually can put it into a water gas shift reaction, which is a very standard technology in the industrial scale, where you put steam and you shift the CO over to CO2, releasing more hydrogen, right? So we're doubling our hydrogen up to almost 80%, 89% of the gas, and then we have CO2. Now that CO2 can be vented because it's biogenic CO2, but in certain locations, like in Europe and other places, we can certainly capture it because they have a value. You can capture it, they can sell it as biogenic CO2. People buy them to make methanol, or they use it in greenhouse feeding or food beverage. So there is a market for CO2 that is biogenic as well.
Got it. Okay. Thanks. We're going to go to the audience. There's one question that a number of different people have asked in different ways, so I'll try to capture it quickly, which is essentially, what is the energy input required to run your plasma torches versus the energy output? That, in a nutshell, that's what a number of different people have asked.
Absolutely, and that's a very common misconception because a lot of plasma system has been used what we call plasma direct melting. So they use all the energy first from the plasma torch. In our case, we call ourselves plasma enhanced, which means that our system is already using an oxidizer. We're using oxygen already. So with the oxidation process, it's already an exothermic reaction, like a standard, autothermal gasification system. So the temperature is already up to 1800, 2000 degrees with the oxygen. And then we enhance it with plasma torch. So the amount of heat that we use to enhance it to 4000 is minimal. We typically use about 165 kilowatt hour per ton of feedstock. So which means for 5 tons an hour, we use 825 kilowatt. And at 825 kilowatt hour, we can generate, 11 tons of hydrogen a day, which means that per kilogram, we're using about 8 kilowatt per kilogram of hydrogen production, whereby electrolysis use 62 kilowatt hour. So you see the difference.
Yeah.
So for a plant like ours, if we build on a 5-acre land in Lancaster, and we generate, let's say, 10,000 to 11,000 kilo a day on 5-acre, if you want to use electrolysis, you need 62 megawatt power to generate the same 10,000 kilo, which means that you need 300 acres of solar panel in order to generate that amount. And that solar panel is not going to operate, all year round. So that's where our cost competitive, that's where we see our fit, is when we are smaller, distributed, when there's not a lot of land, there's not a lot of land for wind farms and solar farms, and where it's closer to the urban area, where there's a lot of waste, and there where the need is, so there's less transportation. So that's a concept behind what we call distributed energy.
Got it. That's very helpful, and I think addresses a lot of the questions coming in because we are very short on time, unfortunately.
I'm sorry.
To one question on the business model from Michael Weber at Engie, and he wants to know if your business model is to sell the hydrogen or sell the intellectual property to make the plants that make the hydrogen. So essentially, are you going to be the owner selling the hydrogen, or are you going to sell the IP?
Yeah, our business plan is a BOO, build, own, and operate them, and own them and sell hydrogen. So we formed that consortium with Fluor to help on the engineering side. We have a consortium inside with a group like Stork, who is doing the operation and management. We work with ABB, who's going to help us with automation. We also looking at using PSA from Air Liquide, so we know that our hydrogen will come out at 99.999%. So we put a very strong consortium of companies that would help us build, own, and operate this plant. And that's a model. We can therefore go out and sell hydrogen and guarantee a 10-year offtake. So the last question that I want to add is we also pull in Munich Re, who is one of the largest reinsurance company in the world, to guarantee the performance of the plant, which means that we're going to tell you we're going to generate 10,000 for 10 years, 10,000 kilo. We will guarantee that. And that is the capacity to get these project financed, because you have a complete performance guarantee.
Right. That's really interesting. One more question on the business model, and then we do need to wrap up, which is what is the cost of feedstock when you're getting to that price of $2? Are you paying for feedstock? Is that how does that all work?
Well, take the Lancaster project. We actually work with the city and take their waste for free. So we essentially will help the city save the disposal costs of landfills. So we assume zero cost for feedstock. We don't buy it and we don't pay for it. And at $0, including amortization of the capex of the plant and the operation, we average $2 a kilo production.
Got it. That's really interesting. So I guess if you do have to pay for feedstock, then the price goes up a little bit. But I have to imagine that,
or vice versa, if we get paid. For example, we're talking to a big Japanese conglomerate who want us to take plastic waste, which is paying a lot of money. And we would love to take plastic because plastic is a huge problem. And our technology is perfect for that. The only challenge is, and you say that, well, you're not really green because it's using plastic. But if we capture that CO2, then we basically generated, blue hydrogen.
Right. Exactly. Okay. Well, we have so many questions, and I'm sorry we can't get to all of them, but the time is up. Robert, thank you so much for
Randy, I just want to quickly say that, they can email us for questions directly to our website at SGH2 Energy, and we'll be glad to answer any further questions. And you can find more information on our website. Sorry about that. Sorry.
No worries. And one person asked if we could share the slide deck. So so email you for that. But so thank you all for joining us today. We really very much appreciate it. Robert, again, thank you. Everyone, I hope you will join us for the next episode of Innovation Stream next Friday, September 4th at 9:30 a.m. Eastern, featuring John Chappell, Director of Business Development for the energy industry at Block Apps, who will be discussing how blockchain can track carbon intensity through the crude oil supply chain. Thanks to everyone who helped put this event together, including Olga Kokova, Zeynep Wirinen, and Roger Morales. This presentation will be available on the Atlantic Council website, YouTube, Facebook, and Twitter. So please do share it with your colleagues. That's it for now. Thank you again, and we're looking forward to seeing you again next week.